All right, next we're going to be looking at chemical bonds, and they're an energy relationship that holds atoms together. When we talk about chemical bonds, we're talking about electrons and their interactions among atoms. When we talk about electrons, we're looking at the subatomic particle that occupies electron shells or orbitals. You can think of these as energy levels, and the closer the electrons are to the nucleus, the less energy they have. So the ones really far from the nucleus in the outermost shell, called the valence shell, they have the most energy, and it's those electrons that participate in chemical bonds. There's this idea called the octet rule, where except for the first shell, which is full with 2 electrons, atoms interact in a manner in order to seek having 8 electrons in that outermost orbital or energy level. So it's all about the electrons and them desiring 8 electrons in their valence shell. There is that exception for smaller atoms like hydrogen and helium that are happy with just 2 electrons in that really close shell because they only have one. But for the most part, we're going to see electrons desire to have 8 electrons, and that's going to be its driving force behind chemical reactions. Now, not all atoms have a full valence shell. Noble gases do. They already have full 8 valence electrons, 2 for helium. So they're not chemically reactive. They're happy with their number of electrons. But many atoms will gain, lose, or share electrons, basically form bonds with other atoms in order to achieve that stability that the noble gases already have. You can see the noble gases here on the far right in dark green of the periodic table. They include helium, neon, argon, krypton, xenon, and radon. And these noble gases are so named because they are inert or unreactive because they're already happy with the number of electrons they have in that outermost energy shell. For example, let's look at helium and neon. Helium is a very small atom. It has one orbital, and so it qualifies as the exception to the octet rule, meaning that it only needs 2 electrons because it has one orbital. Neon has 2 orbitals. That first orbital is happy with 2 electrons, but it also has 8 electrons in its outermost orbital or valence shell. So whereas something like helium and neon are inert and unreactive, something like hydrogen and carbon and oxygen and sodium are reactive. They're not happy with the number of electrons in their outermost valence shell. Hydrogen has 1 electron, it would like 2. Carbon needs 4 more, oxygen needs 2 more, and something like sodium would need 7 more electrons for that outermost shell, or it could lose an electron in order to use its second orbital as its outermost shell that already has 8. So we form bonds when electrons are seeking stability. Electrons are involved in chemical bonding, including ionic bonds, covalent bonds, and hydrogen bonds. Atoms interact and form bonds in order to stabilize their valence shell. So let's look at ionic bonds first. We're going to have an electron acceptor and electron donor. So we're actually going to see the transfer of electrons. And so it could be one or more. For example, you're going to have, when you form salt or sodium chloride, sodium donate an electron to chlorine. Chlorine then becomes chloride and it has an extra electron, making it have a negative charge. That makes it a negatively charged ion called an anion. Sodium, because it donates or gives up its electron to chlorine, now has more protons than electrons. As the electron donor, it now becomes positively charged, and it's known as a cation, a positively charged ion. And the opposite charges that are created with the transfer of electrons between different atoms, that attraction is what results in an ionic bond. Here's that example again, just with pictures. Sodium has 1 electron in its outermost shell. It's easiest for it to have 8 electrons in its outermost shell if it transfers its outermost electron to chlorine. That gives chlorine 8 electrons in its outermost shell, where it previously had 7, and that results in 2 ions, one positive and one negative. But now they're both happy with the number of electrons they have. But because we moved something that was charged, electrons around, the 2 resulting ions have charges as well. A lot of different ionic compounds are salts, and when dry, we actually see kind of a crystalline structure. For sodium chloride, the chlorine and sodium atoms are attracted to each other in kind of this lattice-like structure. But you do see ionic bonds dissolve when in solvents like water, but those charges still exist. All right, we're also going to move on to covalent bonds. They don't transfer electrons, they share them. And when you're sharing a pair of electrons, they get to count for both atoms. You can share 2 electrons, which results in a single bond, 4, which results in a double bond, and 6, which results in a triple bond. And this is going to allow atoms to very strongly bond together, but it also allows them to fill their valence shell at least part of the time. There are 2 different types of covalent bonds, polar and nonpolar covalent bonds. So let's look at examples of a single bond. So we have carbon with its 4 valence electrons, and then we have 4 hydrogens, each with 1 electron, so 1 valence electron. These hydrogens would like 2 electrons, and carbon would like at least 4 more electrons, so they could all be happy with their number of electrons. So if we share a single pair of electrons per each hydrogen, we get to count all of the shared electrons for each atom. So this hydrogen has 2 electrons, so does this hydrogen, this third, and this fourth hydrogen. So they all are happy with their 1 orbital and 2 electrons. Now carbon has more than 1 orbital, so it would like 8 electrons in its outermost shell. And again, when you're sharing electrons, you get to count both electrons in the pair for each atom. So for carbon, we have 1, 2, 3, 4, 5, 6, 7, 8 electrons. So that satisfies the octet rule. Here we have 2 oxygen reacting atoms, and they each have 1, 2, 3, 4, 5, 6 electrons, and they would like 8. So if they share 2 pairs of electrons, they both get 8. So we get to count all 4 of these shared electrons for both oxygen atoms. So you have 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. So both the oxygen atoms are happy. And then last but not least, 3 pairs of electrons being shared, so that is 6 electrons to create a triple bond. So you get 1, 2, 3, 4, 5, 6, 7, 8 for both nitrogen atoms. And so that's going to be able to satisfy these nitrogen atoms, which previously, when they were not in a compound covalent bond, had only 1, 2, 3, 4, 5 valence electrons. Now, depending on how the electrons are shared, the covalent bonding could result in equal sharing of electrons, which produces nonpolar molecules, or unequal sharing of electrons, which result in polar molecules. Also, make sure if you need to review, there are some linked videos to look at ionic and covalent bonds. But let's continue by talking about nonpolar and polar covalent bonding. Here we have CO2, so 1 carbon, 2 oxygen. You can see their arrangement. These atoms are roughly the same shape. They are about the same size, and so when they share electrons, they do so equally. They're going to do so in a way where the electrons can be found or usually located about midway between all of these atoms. That's because the number of positive charges interacting with these electrons that are being shared are not going to be stronger for one atom or the other, so it doesn't create something that's unsymmetrical. It's actually a very linear and symmetrical type of pairing here that we're seeing for a nonpolar covalent bond. Whereas with unequal sharing of electrons, you usually have one atom that is much bigger than the others or other. And that means that the increase in positive protons or charges in that bigger atom are going to exert more of a force on the shared electrons, meaning the electrons spend more time towards that bigger atom. Here we have water, which is 1 oxygen and 2 hydrogen atoms. Oxygen is a much bigger atom than the 2 hydrogens, so when it shares electrons with hydrogen, those electrons spend most of their time near oxygen. So that makes the oxygen side of this molecule slightly negative. We say that is slightly electronegative, and it makes the hydrogen sides slightly positive or slightly electropositive. We call this a polar covalent bond because it creates 2 sides or 2 poles. This 2-pole orientation is oftentimes called a dipole. And so when we're talking about ionic and covalent bonds together, I would say that covalent bonds are stronger than ionic bonds, but we also want to look at covalent bonds more because that interaction between the electronegative an electropositive side of a water molecule, is also important for creating something called a hydrogen bond, where those slightly positive and negative regions interact with other slightly positive and negative regions to create some attraction. So here's a quick guide if you want to come back and look at ionic and covalent bonds. Here we've separated covalent bonds into polar and nonpolar covalent bonds. Make sure you know the basic definitions. For ionic bond, that is the transfer of electrons. For covalent bond, it is the sharing of electrons, with polar covalent bonds sharing unequally and nonpolar covalent bonds sharing equally. So what is a hydrogen bond? I mentioned it briefly as some type of attraction. Well, it's really a weak attraction between molecules, not between atoms. Thus far, looking at ionic bonds and looking at covalent bonds, we've been looking at bonds between atoms. Now we're going to be looking at bonds between molecules. So like two water molecules, for example. This type of attraction, while weak, can be strong in mass or with a lot of these bonds. For example, it's hydrogen bonds that hold the bases of our DNA together. That makes it not only a strong molecule that creates that double helix, but something also that can be unwound in order to be read. So these intramolecular bonds are going to hold large three-dimensional shapes because of this attraction. So here are multiple water molecules. You can see kind of the general layout with the oxygen as red and the hydrogens in gray. So the hydrogens are on the side that is slightly positive, and it'll be attracted to the oxygen of another water molecule that is slightly negative. This interactive force, shown as dotted lines, is the hydrogen bond. The basic definition for a hydrogen bond is a weak attractive force between molecules, generally between hydrogen and oxygen, or hydrogen and nitrogen. So again, that would be responsible for something like a water strider, a bug, being able to skate across a pond. It would use surface tension, the attraction among water molecules, in order to do so. All right, next we're going to be looking at chemical reactions and chemical equations and looking at different types of reactions. So make sure to watch that video.